In this set of problems, we'll be looking primarily at hypothesis tests for means, of course, with some other things spiraled in. Number 1, a pharmaceutical company claims that a medicine will produce a desired effect for a mean time of 58.4 minutes. A government researcher, so there you go, that's the claim, is 58.4. A government researcher runs a hypothesis test of 40 patients and calculates a mean of 59.5 minutes with a standard deviation of 8.3. What is the p-value? So first of all, our standardized test statistic is the statistic minus the parameter. Our parameter is 58.4, and our alternate hypothesis, it doesn't really give one way or the other, and you don't use the sample to decide. We just assume that it is not equal to 58.4. Our degrees of freedom is our sample size minus 1, so we have degrees of freedom of 39, which pretty much tells you it is either A or C. And of course, we can calculate our standardized test statistic using this formula, 59.5 minus 58.4 over 8.3 divided by square root of 40. And you can see actually all of these match in the center. So again, we're just down to A and C. What is the difference between the two? Well, one's appropriate for a two-sided hypothesis test, while the other one is just a one-sided hypothesis test. Since our alternate does not equal 58.4, we're doing a two-sided hypothesis test, and the answer is C. 2. The greater the difference between the null hypothesis claim and the true value of the population parameter, A, the smaller the risk of type 2 error. So we're looking at risk of type 2 error and power and how those change. Okay, so we're going to go ahead and look at the difference between the null hypothesis claim and the true value. So I need to show an alternate. So this is the hypothesized, and I can click this here on the applet. And first of all, we'll just, let me unclick these two right now. So basically, you have your hypothesized value and you have the real value. We're assuming, we're looking at type 2 error and power, so that means the alternate is true. And it asks about the difference between this true value of the mean compared to our hypothesized value of the mean. So power is our ability to jump to the other side. And in this case, you can see this is the power, all right? The probability of type 2 error is 1 minus the power. So here you see type 2 error is 0.737, and the power is 0.263. If you add these two up, they should always add up to 1. So as I slide this over, my curve, more of my curve, or my sampling distribution, moves into the power section, and less is in the type 2 error. So as the true mean and your hypothesized mean become further and further apart, in other words, the greater the difference, the greater your power and the smaller your chance of type 2 error. Okay. So the correct answer is B, the smaller risk of a type 2 error and the greater the power. All right. Number 3, a factory is located close to a city high school. The manager claims that the plant smokestacks spew forth an average of no more than 350 pounds of pollution per day. As an AP statistics project, the class plans a one-sided hypothesis test with a critical value of 375 pounds. So they're telling you where they're going to make up their mind. If it's 375 or more, they're going to reject this null, all right? If it is less than 375, they will fail to reject and they'll accept what the factory is saying. Well, we never accept, but anyways. So this is a one-sided hypothesis test with a critical value of 375. Now we know, or at least we're saying the true value, at least the true standard deviation and the true mean is actually 150 pounds in standard deviation, and the true mean is actually higher, 385 pounds. If the sample size is 100 days, what is the probability that the class will mistakenly fail to reject the factory manager's false claim? So we need to create a sampling distribution. The mean is actually 385. That is reality. And if we're doing an average over 100 days, we take that 150 and we divide it by square root of 100 and we get 15. So that's what the model looks like. If we are higher than 375, we reject. If we are lower than 375, we fail to reject. So we're looking at the probability in the shaded area. which means we want probability that X bar is less than 375. And here's a normal CDF with a low negative infinity to 375, the mean of 385, and a standard deviation of 15. So we're going to find the probability the mean is less than 375. Using a normal distribution, we're going to hit second distribution, so second vars. Make sure you go to normal CDF, which is 2. And you can see I already went ahead and I put in the negative infinity. That's negative. Here, I'll show it to you again. Make sure you hit the negative sign, not the minus sign. 1. And then to get to the EE, hit that comma. It only gives you 1 E. That's fine. 99. And then you have 375, 385, and 15. And then hit enter. And there is your answer, 0.2525. So we get 0.2525, which means that B is the correct answer. Number 4, which of the following is most important in minimizing the placebo effect? We talk about, so to minimize a placebo effect, the subject should not know which treatment they are receiving. That's called blinding, all right? We also need to compare it to people who received the placebo instead of the other treatment. They are the control group. So we need blinding and a control to minimize the placebo effect. Randomization is good, but that's more for confounding variables. Number 5, to which of the histograms below can the box plot correspond? So you can see, first thing I notice is the median is 50, which means half the data has to be to the right of 50 and half has to be to the left of 50. So you can see that if I want a median around 50, that eliminates C, D, and E, which all have more than half of the data to the left of 50. So now I'm only with A and B, and I need, I can see that my whisker goes up to 60, so that eliminates A because the highest data point is at 55, maybe. We don't even know that it goes up there, but here we see roughly that we can go up almost all the way to 60. So the correct answer is B. Number 6, which of the following is a true statement? A, the sampling distribution's p-hat has a mean that can vary from the population proportion p by approximately 1.96 standard deviations. Actually, sampling distributions should have the same mean as the population, so this is false. B, their standard deviation is close to square root of n times p times 1 minus p. That's actually the standard deviation for a binomial distribution, not p-hat, so that is false. C, the sampling distribution of p-hat is considered close to normal provided the sample size is at least 30. At least 30 is for means, not proportions. This is false. D, the sample proportion is a random variable with a probability distribution. Yes, it is. That's true. The probability distribution is approximately normal if all conditions are met. Now, it didn't include that, but that's true for the proportion if all conditions are met, and D is correct. A guidance counselor wishes to determine the mean number of changes in academic major by college students within plus or minus 0.1 at a 90% confidence level. What sample size should be chosen if it is known that the standard deviation is 0.45? So we know standard deviation is 0.45, our margin of error is 0.1, our confidence level is 0.9. What should n be? So I'm going to go ahead and bring up the margin of error formula, and we're going to use Z star. Typically, we would use a T star, critical value, but since we don't have a beginning sample size, we're going to use Z, which is inverse norm. It says inverse Z, sorry. Area of 0.9 and a center of 1.645. So to find the critical value, we go second distribution. We're using inverse norm because we don't have a sample size to start, even though we're working with means, and that should be fine. Hit enter. We have a 95% confidence interval, so we want the area to be 0.90. Keep the mean of 0 and 1. Make sure you hit center, and you get 1.645. And just to refresh for those of you who may not have the fancier calculators, if you do inverse norm, remember that it defaults to left. So we have to make a slight adjustment to it. So if we have 90% in the center, we have 10% left over, right? And half is on the left and half is on the right. So I'm going to add that 0.9 plus half of that 10, which is 0.05. And then if we do that, we should get the same critical value of 1.645. So now we can go ahead and substitute all our values. We have 1.645 for the critical value right there. And then we have 0.1 for the margin of error. See, there's the 0.1. 0.45 goes here because standard error is the standard deviation for the samples that we have divided by the square root of n. So then I'll go ahead and multiply these two numbers out, which gives me 0.74025. Then I can divide, cross multiply basically. Square root of n comes up here, 0.1 comes down there. Go ahead and divide and then square both sides. So we have 54.8. Always round up. Even if that was 54.1, we would still say 55 or C. Number 8. The sampling distribution of the sample mean is close to the normal distribution. Well, from our G3 activity, sampling distributions for means, or your G3 notes, we talked about how you could have a normal population and a non-normal population. So if your population is normal, it doesn't matter how big your sample is, your sampling distribution will be normal. But if your population is not normal, if your sample size is at least 30, then it will be approximately normal. So if n is large, no matter what the distribution of the original population, then we are close to the normal distribution. So for n is 30, we know it's true for both, regardless of what we started with. Number 9. 500 people used a home test for HIV and then all underwent more conclusive hospital testing. The accuracy of the home test was evidenced in the following table. What is the predictive value of the test? In other words, what is the probability that a person has HIV and tests positive? So basically, we have probability of positive and HIV, so we count how many are positive and HIV. There are 35 positive and HIV right here out of a total of 500, which is 7 over 100 or 0.070. Number 10, what is a false positive rate? That is, what is the probability of testing positive given the person does not have HIV? So we're in this column right here. So probability of positive given not HIV is positive and not HIV. So that would be the 25 up here over the 460, or basically 0.054. Number 11, what is the sensitivity of the test? That is, what is the probability of testing positive given that the person has HIV? So positive given they have HIV, well, there are 35 that have tested positive out of the 40, which is 7 over 8. Or 0.875. Number 12, what is the specificity of the test? That is, what is the probability of testing negative given that the person does not have HIV? So we know that they are in the healthy column. And of those testing negative, we have 435 are negative and not HIV out of 460, which works out to 0.946. Question 13, which of the following statements is false? Like normal distributions, t-distributions are symmetric. T-distributions are symmetric, but more spread out than normal distributions. Both A and B are true. Number C, the greater the degrees of freedom, the closer the t-distributions are to the normal distribution. So, and also we have the smaller the degrees of freedom, the better the 6895-99.7 rule works for t-models. So we'll explore both of these. Okay, this is a t-distribution with a degree of freedom of 1, which means a sample size of 2. And the question is, the greater the degrees of freedom, does this get closer to the normal? And as you can see, it does. Which means that the greater the degrees of freedom, the more it looks like a normal distribution. C is true and D is false. With smaller degrees of freedom, the less it looks like a normal distribution. So the empirical rule would not work as well. And then finally E, the area under all t distributions and other valid probability distributions is always 1. So E is true. So the only one that is false is D. The smaller the degrees of freedom, the better the empirical rule, which is not true. Number 14. The dot plot is for a set of numbers. One element is labeled X. Which of the following is a correct statement? So I'm going to say X is near the mean, so it has a small z-score. So A is incorrect. It does not have the largest z-score. Then B mentions box plots, and it will plot an outlier like X is an isolated point. Box plots never have outliers in the middle of the data, so they're always on the extremes, so this is incorrect. A stem plot will show X isolated from two clusters. That is correct. You would see that on a stem plot. D, because of X, the mean and the median are different. Actually, the D is incorrect. X is not skewing the mean. It's not like a high outlier or a low outlier. And then E says the IQR is exactly half the range. Well, IQR is going to cut out the middle 50% of data. So I'm going to say that's roughly the IQR. Could be a little more, a little less. But basically, that's bigger than half the range. So E is incorrect. So the correct answer is C.